I would like to thank the organizers, Professor Jiang, Professor Kassaman, for inviting me here and to give these lectures on the trace formula. So let's get started. So this is the stable trace formula. With emphasis on SL2. So let me give the brief outline of what I will do in the plan. So first I will talk about the Cocompact case, very briefly. We will define the kernel and its truncation. So which is the absolute convergence of the kernel is theorem 6.1 in Arthur's notes. And so then I will talk about the geometric expansion of the kernel, followed by the spectral expansion. And finally, we will talk about I will talk about the invariant trace formula. And finally, I will talk about the absolute convergence of the trace formula. And some applications that we hope for beyond endoscopy. This will also be very brief. So this is the plan for the next couple of days. And so this is a lot. This is a lot. I mean, this is ambitious. If you look at Arthur's notes, they are like over 200, 250 pages for when he develops this and more. So after this, Tasho will follow with the stable trace formula. Okay, so that's one thing. So this is a lot, but we will have the example of SL2 to help go through all these technical aspects of the trace formula. Yeah. So let's start with the Cocompact. Let me briefly tell what the plan is. So basically, the trace formula is a identity of two distributions. So you have the geometric side equal to the spectral side. So f here is a compactly supported smooth function, support on the adelic points of a connected deductive group, and you write G here to denote the dependence on the G. And it's basically an identity of distributions. You put in a test function, get something out of it. And typically you use this for comparison. So Arthur develops this trace formula and then modifies it accordingly so that he can compare the trace formulas on different groups. You compare the geometric sides, get some information on the spectral sides, and so on. But that's not the only use of the trace formula. Also, in isolation also it can be used. And it gives important results like while law that Selberg originally proved. So we will always take G, I mean not always, whenever I say G is SL2, we will have this example at the back of our mind, and so explicitly we will do these computations for SL2. Now so SL2 has rank 1, so there are some simplifications happening, okay? But it's a good example anyways. There are some combinatorics are simplified because of being SL2, but it lets some other aspects shine, okay? All right, so this geometric expansion looks something like this, O in O, G O of F. There are some equivalence classes here, and similarly the spectral side looks like chi in some X classes, G chi of F, okay? Yeah. All right, so this is like a very brief introduction. Now let's do the Cocompact case. So there are two reasons I decided to explicitly do the Cocompact case, and that is, one thing is that it gives a good initial feel of what is going on, and secondly, if you look at the invariant trace formula, the easiest terms in the trace formula for the geometric as well as the spectral side, those are the terms that correspond to G, the Levy subgroup, full group G. They are exactly the terms that appear here. Okay, so that's one motivation why this is why we need to learn this. So let H be a unimodular locally compact group, and let gamma be a discrete subgroup. In H, and you consider the right regular representation of H on the L2 space of H mod gamma. And how you decompose this, so the action is given explicitly by Ry phi. This is the function evaluated at x gives you xy, usual right regular representation. Now, how you decompose this kernel, this R, is a very important problem in this area. So the question here, to decompose this R into irreducible unitary components. Okay, so what basic example, if you take H equals R, you get take gamma equals Z, discrete subgroup in R, and then the R, the right regular representation, decomposes discretely into, so indexed by lambda in 2 pi I Z of those representations. Lambda x. So these one-dimensional representations, and this is explicitly done by the Plancherel theorem. So for Fourier series, so this R, so this L2 R mod Z under the action of R is isomorphic to L2 of L2 Z, yeah, namely the Fourier coefficients. So this, if you have phi, this is phi hat, where phi hat of n is integral phi of x e to the 2 pi I nx dx. And the Plancherel theorem says that this is an isometry. Plancherel. Okay, so you know exactly how this the L2 spectra, the right regular representation decomposes. Another standard example is when you take Z to the trivial group, H is again R, gamma is the trivial group. And in this case, you get Fourier transform, okay? So R decomposes continuously. Via Plancherel theorem for Fourier transforms. And explicitly, this is given by, the isometry is that f, the norm of f, is the same as the norm of its Fourier transform. And so f hat is the Fourier transform. Okay, so you know exactly, and in general, these are the two extreme cases, when you get compact and when these are the two extreme cases, and in general, what happens is that R decomposes as a direct sum of a discrete representations and a continuous spectrum. Okay, so in the first case we had this thing, in the second case we had this thing, and in general it's a mixture of two. And then the main theorem here is of Langland's, like he tells the spectral decomposition and Eisenstein series gives you exact how like this. The Langland's theorem of spectral decomposition explicitly tells you how this isomorphism works, and more concretely how the spectrum. It gives you much information, a lot of information about the spectrum here. Okay, so now to study the R, the right regular representation, you study the operators R of f, where f is a test function or f is a function. So to study R, we study the operator R of f, and you impose some restrictions on f, so that f is in L2 of h mod gamma. And so you study this operator here, and you want to find what the trace is. So this R of f, if by definition it's the integral f of y, ry, dy, very standard these things. And you want to know what the trace of so what I mean here is that R of f acting on a function phi evaluated at x. So this is the integral over h f of y. R of y evaluated at phi is phi of xy dy. And now you decompose this. So first of all, you make a little change of variables and write this as f of x inverse y, phi of y, dy. And then this integral over h you break as an integral over h mod gamma and sum it over gamma. So y, you replace y with gamma y. So you have f of x inverse gamma y, phi of gamma y, dy. But then phi is invariant on the left by gamma, so it's just phi of y. And so this is nothing but integral of h over h mod gamma of kxy, phi of y. dy, okay? And the k is explicitly, this is the kernel here, okay? So this is an operator which has a kernel. We want to understand how the R, we want to break R, so we look at this test function f and look at the operator R of f, take the trace. I mean, there are conditions when you can take the trace. I will get there very shortly. One thing to note here is that the sum in the k definition of k is finite because of our assumption that f is compact. So gamma is a discrete subgroup. The support of f is compact, so there are finitely many points. This is a finite sum. Okay, now I have to make the big assumption. This is the co-compact case. So I will assume that gamma h mod gamma is compact. This is a very serious assumption, and this is very special. This is hardly typical. So now if I assume this, then two things happen here. The first is that kxy is compactly supported. Which means that it is square integrable. And if the kernel is square integrable, the operator is, so this operator Rf is Hilbert-Schmidt class. And so in particular, it is compact. Now if you have a compact operator, you have the spectral theory. which tells you that this decomposes into discrete spectrum. So you can write R as a direct sum over so pi with a multiplicity. So finite multiplicity, m pi r is the multiplicity. There are isometric copies of pi. How many? These many copies of pi. As pi varies over all representations, and you have finite multiplicity. This thing, okay? So this is one conclusion of this assumption. The other is that you can take a trace. So second is that RF, this operator, is of trace class. So you can take the trace, and trace of R of f is a integral of kxx. Integrate along the diagonal, you get the trace. This is the conclusion. And if you combine these two statements, then you get that you can write the trace of R of f as a sum overall trace of pi of f with a multiplicity. Okay, it just follows from this decomposition. You can just add up. Okay, and so this is I will write this as a sum over pi. I will denote this by a gamma h pi, the multiplicity, and this I will denote by f h of pi. Okay, and this is your spectral side. This is the spectral side, and correspondingly, if I play around with this expression of this as integrating over the diagonal, then I will get the corresponding geometric side. So let gamma, I mean this parenthesis gamma, denote the representatives of conjugacy classes in gamma. So if gamma is abelian, this is just gamma, this set. And for let omega gamma denote the centralizer of gamma in omega, where omega is any subset of H. Okay. So then I look at the trace, this equation here, trace of R of f, which is nothing but the integral over the diagonal of the kernel. Now I break this into so this, by definition, the kxx is nothing but a sum over gamma of f of x inverse gamma x dx. This is the definition of k. So now I break this gamma in gamma into the conjugacy classes. So gamma is in a conjugacy class, and then I sum it over conjugacy classes. F of x inverse delta inverse gamma delta x. Okay, so if I do this, there is some 2 or 3 steps simplification that happens. No. F is compactly supported smooth. Yeah, let's stick with this assumption. Yeah, function on H. That's right. Yeah. Yes. Yeah, function on H, of course. Yeah. So now, yeah. So what happens here is I can combine the integral over H mod gamma and this sum over gamma mod the centralizer of gamma and write it as integral over centralizer of gamma of the sum over gamma in gamma of f of x inverse gamma x dx. I'm combining this delta with x, okay? And then I break down this as an, so let me write this as a sum outside. I break this again now into h mod h gamma and h gamma mod gamma gamma f of x inverse du dx. All right. Now, u inverse gamma u is nothing but gamma because u belongs to h gamma, so centralizer of gamma. So this I can combine and write gamma in gamma, integral of h mod h gamma f of, and I will have a volume term. So this is the volume of this term. Of the integral over h mod h gamma of f of x inverse gamma x dx, because this is nothing but gamma. That's what is happening. And so I can write this similar to the spectral side as a sum over conjugacy classes of a gamma h of gamma, which is nothing but the volume, times fh of gamma. So this is the geometric side here, okay, and this is the spectral side. So this is the trace formula for the compact quotient, okay. So initially it was Selberg who used this. Who modified, this is initially for a quotient to be compact, gamma, h mod gamma is compact, but Selberg modified it for SL2, and he used this to show the existence of mass forms via the Weil law, and this is, so here gamma is a congruent subgroup inside the SL2, and also Jacquet-Langlands used this for GL2 to prove they used the comparison of a trace formula on two different groups, GL2 and its inner forms, the quaternions, and then they compared the geometric side and got the information about the automorphic representations of GL2 and the quaternion algebra, okay. So that is those things we know. I mean, that gives you the motivation to give a more general trace formula than the compact quotient case, okay. So now the next part here is to head towards or build towards the truncated kernel. So if you naively apply this kernel to the case when h mod gamma is not compact, things go wrong or bad, and then Arthur modifies the kernel and shows some finiteness results, and then develops the geometric as well as the spectral expansion from that modified kernel, okay. So there will be quite some notations here, so bear with me while I write those notations, okay. So they are pretty standard, but let me just do it again, like do all those notations. Okay, so G is a connected reductive group. So I will everything works for any number field, but I will stick to Q, okay, just for simplicity. Like Archimedean, there's only one Archimedean, I'll say real place and so on. And that's just for convenience. And so you can think of G as SL2. Arthur, when he gives these notes in the clay notes, he does the case of SL3. And that is also quite instructive because a lot of combinatorics and geometry, which is trivial here, you can see that for SL3. Now here, AG is the largest center, this is this standard. Subgroup of G, which is also Q-split torus, and xg is the set of characters, and this is the vector space AG is x hom xg. So Q hom xgr, okay, z whatever. AG star is xg tensor with R. So these are real vector spaces. And I will denote this. This is not Arthur's notation, but this is the notation of Labesse and Vosperger. So A is the AG, R, the connected component. So this is like copies of the real line, okay? I mean, if you apply the exponential map here, you get the real line, but okay. And then I define the Harishchandra map, HG. This is a very important map. So HG is from GA to AG, and HG defined at a G. So these two vector spaces are dual to each other, okay? And so you find the value inside AG by evaluating it at any element of XG. And define this to be the log of mod chi of G. So for all chi in this is the definition. And you denote the kernel by GA1. Okay. So then you have a direct product. GA is GA1 times AG. So basically the reason you are defining this map is that you want the volume of GA mod GQ to be finite. But there are some copies of R sitting inside which don't give you finite. So you mod out by these copies of the real line or the split torus, and then when you take the quotient by GQ, then you get finite volume, okay? Is that okay? Alright, so for SL2, this is trivial, like there's not much happening with SL2. I will write this in blue chalk. So for G is SL2 if I take, then many of these objects are trivial. Yeah, and AG is AG star, it's just a zero vector space. So GA1 is GA, because there is no center, and so on. So AG is 1 or 0 or 1. Okay. So now the next thing is to choose a parabolic subgroup. So, and everything is happening with respect to that parabolic subgroup. So I will choose a minimal parabolic subgroup. So choose P0 okay, and you say that P is standard if it contains P naught. All right. So now, where am I? Yeah, now I choose a maximal compact subgroup. So let me do this for SL2. So for P a prime, let Kp be SL2Z and K infinity be SO2R. And then you form the product K, which is K. Sorry, thank you. K infinity is the product over P of Kp. So this is the maximal compact subgroup inside GA. Which is nothing but SL2A here. And then you using this K, you extend, let me say, in general, this is for SL2. So in general, the way you choose the K is as a product of KV over all places V. And you, in the Brouhardt's building, you fix a special point, and corresponding to that special point, you get a. There are some technical things about how you can attach this K, get this K. But Arthur explains that. He calls it good subgroups. Okay, good maximal compact. Okay. So using this K, I extend the map HG, which is initially defined on GA. So take P to be a standard parabolic. Its Levy decomposition is MP, NP. Or NP, MP, depending on, fix one, but let's fix NP, MP. And you have the Iwasawa decomposition, so GA is PA, K, this is the Levy decomposition, this is the Iwasawa decomposition. Using this, you extend the map HG, you define the map HP, in the following way. So HP of any element G is HP of, if I write G as NMK, then this is nothing but, by definition, H MP of M, where M belongs to MPA, N belongs to NPA, and K belongs to K. Okay, you given a G, write this, and then only it depends on the M part. And here you know HMP of M you already defined by replacing G there with MP. It's a reductive group. So this is how you extend the map HG to HP. Okay. And then now let me write the expression of the kernel for non-compact case. So if you have G to be GA1, sorry, in the previous notation, if I have H and gamma, so if I take H to be GA1 and gamma to be GQ, then GQ is a discrete subgroup inside GA1. So if you just naively write the previous expression of the geometric side as a sum over conjugacy classes gamma, then of the volume, there's a volume term, GQ gamma. Then two things can happen. Either this integral can be infinity, or this volume can be infinity. And both bad things do happen. Okay, so either this can be infinity or this can be infinity. And even for G equals GL2, these they both may diverge. Yeah, both do diverge. So Arthur gives an example. He just does some computation for G equals GL2, and this is. So let me write this sentence. Both diverge. Yeah, and the reason they diverge is because of the existence of parabolic subgroups inside this. If you have the compact case, there were no parabolics. The abelian case, there are no parabolics. And that is a classical theorem of Borel and Harishchandra that says that the quotient is non-compact precisely when there exist parabolic subgroups. So this theorem says that GA1 mod GQ is compact if and only if there are no parabolic subgroups, non-trivial. There are no non-trivial parabolic subgroups. Okay. So then Arthur, when he defines the modified kernel or the truncated kernel, inherently it's an alternating sum indexed by the parabolic subgroups. Okay. And the thing about the modified kernel is that it agrees with the original kernel, what you expect to be the original kernel in a compact neighborhood of the identity or 0. Okay, so that is the approximate kernel, the truncated kernel. I will write that expression. Before I write that expression, I will have some more notations that will help me to write that expression. Okay. So this is, yeah, so this gives us to the next part, which is the kernel and its truncation. Okay, so some more notation. Take P1 and P2 to be standard parabolics. So you get an embedding of AP1, figure is AP2. AP2 sitting inside AP1, and AP1 sits inside MP1, the Levy subgroup of P1, which sits inside MP2. And this gives you an embedding of the character groups X MP2Q, X MP1Q. And because of this, two things happen. You get AP2 star sitting inside AP1 star, and the second is AP. So AP means AMP. Okay. So AP1 surjects onto AP2. So AP here is AMP. Okay, I know what AMP is because of this AG I know. So I know AMP, and so this is the definition. And because of the characters of AG, so now I will define lots of vector spaces, and I will define bases of those vector spaces, bases of those vector spaces. Okay, and there are pairings on those bases. So the other map, X, AP1, Q, surjecting onto X, AP2, Q, gives me two more maps, AP1 star, AP2 star, and AP2 sitting inside AP1. Okay, so the whole upshot of this is that I get two exact sequences of vector spaces. Okay, I will define the kernel and the co-kernel of those. So I get two exact sequences. Let me write those exact sequences. Two split exact sequences. So 0. So this is the definition. By definition, this is the kernel of this map, and the other one is the dual space. So by definition, this object and this object, they are what make the sequence split exact sequence just define this to be this mod this and so on. Okay. Yeah. So now roots. Okay. So this is the two split exact of our vector spaces. Now I will define the roots and co-roots and weights and co-weights. So phi p, let phi p denote the set of roots in PAP. And I'm calling it a set because it need not be the root system. So and identify phi p inside AP star by phi p x of AP Q sits inside x AP tensor R, and this is nothing but AP star. So you can think of this finite set sitting inside this vector space, and it actually no, actually it does not span. Let me not complete that set. So yeah, if P is P0, there are minimal parabolic subgroup, then this is a root system. And you denote delta 0 to be the set of simple roots. Now you have made the choice of a minimal parabolic. So then once you made that choice, then you can write the simple roots. In phi 0. And delta check is the simple co-roots. And they're sitting inside delta. They are sitting inside the AP and AP star, and you have the notion of the weights and co-weights. So weights are the basis dual to these simple co-roots, and co-weights is a basis dual to these roots. So in the end, there are 4 objects: roots, weights, co-roots, and co-weights. So delta 0, so delta 0 hat check is co-weights. Dual to delta 0, and delta 0 hat weights dual to delta 0 check. Okay. So in short, you have delta 0 and delta 0 hat sitting inside A0, and delta 0 check, delta 0 hat check sitting inside A0 star. Okay. And there is a duality. These are the dual bases, and these are the dual bases. Okay. Now, let me. So, the theory of connected deductive algebraic groups gives us a bijection between finite subsets of these and standard parabolic subgroups. Okay. So, P containing P0. This set is in bijection with delta 0p as a subset of delta 0. And the identification is by the definition of AP, which is in this case H in A0, which vanish in this set. Okay. Now, you define delta P. So similarly for a P, I will have some more bases of the vector space AP and AP star. So you have delta P is, you think of this as delta elements of delta 0, the complement of this in this. Okay, but then it's a restriction. So a linear forms on AP there's a subtle point here, that is the restriction obtained by restricting elements in delta 0 outside delta 0p to AP. So initially these are defined on A0, which is a bigger space. You restrict it to A where it is not 0, and that is exactly AP here. Okay, so AP is sitting inside A0. That's what I'm saying. All right. They vanish on other part than AP. So they vanish on A0p. Forget that part. You consider them as here. Okay. So now once you do that, you can you'll have 4 more objects. So delta P check will be defined by as alpha check, alpha in delta P, and you similarly have delta P hat, which is the dual basis of this, and delta P hat check defined similarly. Okay, so they are again the basis of AP and AP star. Okay, those 2 vector spaces. Let me do one thing. For SL2, let me compute these. There's not much happening because there's only one P for SL2. We saw that AG is trivial. AG is just 1. AG is 0, and AG star also is 0, and so on. But then the set of, you have two parabolics, two standard parabolics. So fix P0 to be this inside SL2. And then there's only, the other one is G. So two standard parabolics. P0 and G, okay, that's it, rank 1. So yeah, AG there's nothing, but A0 you have, it's a non-trivial real vector space, A0. A0 is nothing but AP0. And you can have beta 1 is E1 minus E2, where EI of T1, T2 is TI, and T1, T2 is 1. Yeah. So beta is TT inverse, so that is, so beta 1 of TT inverse is T square, and so on. So there's only one root here. So delta 0 is just beta 1. And the other one is pi 1. That's nothing but beta 1 over 2. Convince yourself that this is the case. And similarly, you have delta 0 check is beta 1 check, E1 check minus E2 check. I'm just setting up notation, okay? This is, yeah, you just convince yourself that all this is very standard. EI, EJ check is delta IJ, and beta 1 check is 2, and it's a different bracket. And finally, delta 0 check hat is pi 1 check is beta 1 check divided by 2. Okay. Yeah. So this is the only thing. Now let me define the characteristic function. So Arthur does truncation. So he needs some characteristic functions to cut out some parts inside the A0 vector space. So let me define those characteristic functions. So for P standard parabolics, define tau P to be the characteristic function of the set inside AP. It is the set of T in AP. Alpha of T is 0. This. And similarly define tau P hat. Once you get used to this notation, it will seem very smooth, harmonious. Okay, so this is the same thing, except you replace delta P with delta P hat. Okay. Sorry, what am I writing? Alpha of T is greater than 0. Yeah, of course. Yeah. Yeah, thank you. Now you define a point, say T in AP is sufficiently regular if it is away from the walls of inside AP. So if alpha of t is far off from 0 for alpha in delta p. The picture here, SL3 provides a better picture than SL2. Okay, so in this case, if you look at SL3, then these are the walls, and if you want T to be far off from the walls and so on. But I don't want SL3 here. Let's stick with SL2. And in SL2, there's not much. A point is regular if it is away from the origin. So there's only one. A0 is the largest space, the real vector space. For SL2, A0 is the span of beta 1 check, which is the span of also pi 1 check in that notation. And regular means T regular precisely means it is away from the origin. Okay, the wall is the origin, so it's away from the origin. Now, there's one ingredient I need before I define the truncated kernel, and that is the right regular representation when you take into account the parabolic subgroups. So, let me just define that. Yeah, positive, this is greater than 0, right? Yeah, sorry, yeah, away from the origin towards the positive. You're right, you're right. Positive, how should I write it? You know what I mean, right? So beta of t is greater than 0. Yeah. So this is 0 and this is beta 1. And you want, beta 1 check. So yeah, a positive away from the origin. Plus, yeah, just keep that in mind. Yeah. This is not so serious, okay? Yeah. So let me define the kernel now. Kernel of the representation. So Kp, Kg, Kp. Let me define these objects. So you have Rg, the representation of Ga on the L2 space of Ga mod Ga1 mod Ga mod Gq, it doesn't matter. Yeah. So this is Rg, phi evaluated at y is Rg of y evaluated a vector phi xy. And similarly for any parabolic p, maybe not standard, so for p parabolic, you have a map K, this is the space, the correct space to look at is, so let me define xp as the space NPA, MPQ, GA, and the representation RP, again it's a induced representation of G, given by the same action, Rp of y phi x is phi of xy, and it is nothing but the induced representation from Rmp. So the right regular representation of on the MP, you extend it all the way to G. So Rp is induction NPA, GA, the trivial on NP, and RMP on the MP part. Okay, so this you define, and then this the kernel of RP has this expression KPXY. If you have KG, the expression is summing over all gamma of f of x inverse gamma y or x. So here you have to integrate over NPA and then sum over MPQ f of x inverse gamma ny dn. see, if you have P equal to G, then you get this discrete sum over GQ. There's no integral in that case. All right? Okay. So yeah. Let me, give me just one. I will stop. Okay. Let me stop now. So next thing I'm going to do is define the truncated kernel as an alternating sum over all standard parabolic subgroups. Okay. And then spend some time about its absolute convergence and so on. And from that truncated kernel expression, Arthur develops the geometric expansion from that and the spectral expansion. Okay. So I will stop here. I wanted to write the expression for KT, but I will restrain myself and I will stop. Okay. So thank you. Yeah.